If you have to cross half of a distance before you reach your destination, and half of that distance before you get there, and so on and so forth, when do you ever take your first step? Let's consider. Hello, philosophers. I'm Chico. Welcome to the Philosopher Show, where we consider the greatest questions of human history. Back in the very beginning of this playlist of infinity, we saw a guy named Zeno of Elea, and we looked at his paradox of Achilles. Now, that said that Achilles could never catch up to the tortoise because every time he got to where the tortoise had already moved a little bit, and so infinity created an unlimited number of catch-up points. Zeno actually had 40 paradoxes. Not all of them survived, but the one that we're going to look at today is possibly more disturbing than the one about Achilles. If the Achilles paradox says that you can never finish a race, this paradox is going to say that you can never start one. It's called the dichotomy, from the Greek word for cutting in two. Today we'll look at two forms of this paradox and also what calculus has to say and whether calculus can actually answer the question in the first place. First, the progressive form. Here's the setup. You walk across a room. Before you walk across the room, you have to walk halfway across the room. Before you walk halfway across, you have to walk a quarter of the way across the room. And you can keep going like that all the way to infinity. Every distance you have to cross has a smaller distance that you have to cross before getting there. So there is no first distance to cross. And that's because every candidate that you give for a first distance to cross, you can always cut that in two again. Now think about what that means. To walk across a room, you need to complete an infinite number of sub-journeys. And this infinite series does not just happen to be long. It has no first member. It's like being told to count backwards from infinity before you can take your first step. Where do you start? Infinity? Then what? 9999999? There's actually no first step that you can take. Here's an analogy. Imagine you want to flip a light switch. But before you can flip that light switch, you have to flip a light switch that is smaller than it. And before you can flip that smaller one, you have to flip an even smaller one. And then there's always another smaller switch that you have to flip first before you can flip whatever switch that you're looking at. You'd stand there forever with your hand raised, never being able to do anything. That is what the dichotomy does to motion. That's the progressive form of the paradox. You're trying to move forward, and an infinite regression of prior steps stops you from beginning. Now let's look at the regressive form, which comes at it from the other direction. Suppose somehow you do start walking. You make it halfway. Great. Now you have to cross the remaining half. But before you get there, of course, you have to cross the half of that, bringing you to the 3/4 mark. Then half of that, which brings you to the 7/8 mark, and so on. You keep getting closer, but you never arrive. You always have half the distance remaining to go. This version is actually very similar to the Achilles paradox. In both cases, you're making progress through an infinite series, but you're never completing it. So the dichotomy hits you sort of from both ends. The progressive form says you can never start because there is no first step. The regressive form says if you do start, you can never finish because there's no last step. Together, they seem to prove that motion is completely impossible. And yet, here I can walk across any room that I want. So what went wrong? The standard textbook answer is that calculus solved this problem 300 years ago. And if you've taken a calculus class, you've probably heard about a convergent series. Here's the idea. Yes, you have to cross an infinite number of distances, 1/2 plus 1/4 plus 1/8 plus 1/16, and so on and so on. But the sum of this infinite series is not infinite. It converges to exactly 1. The mathematical proof is elegant. Call the sum S. Then S equals 1/2 plus 1/4 plus 1/8 plus 1/16, and so on and so forth. Now, multiply both sides by 2. You get 2S on the left, and then you get 1/2 times 2 is 1, 1/4 times 2 is 1/2, 1/8 times 2 is 1/4, 1/16 times 2 is 1/8, etc., etc. But now look at everything on the right side of the equal sign besides the 1 that exists there now. You have the 1/2 plus the 1/4 plus the 1/8, etc., etc. Well, that's just the original S, right? So what you really have on the right-hand side, you can write it as 1 plus S. So now 2S equals 1 plus S. Subtract S on both sides. On the left, 2S minus S is just S. On the right, 1 plus S minus S is just 1. So you get S equals 1. That's your sum right there, S equals 1. So the infinite number of subdistances add up to a finite distance. You cross all of them, and you've crossed the room. Problem solved, right? Well, the same logic applies to time. If each sub-journey takes proportionally less time, half the distance at the same speed equals half the time, then the infinite number of sub-journeys is completed in a finite total time. The entire infinite series gets packed into, say, 10 seconds. This is a beautiful result, and it's mathematically correct. But does it really solve the paradox? I want to suggest that it doesn't, at least not by itself. Here's the issue. The calculus answer tells you what the sum equals, but it does not tell you how a physical being actually completes the process. Think of it this way. Saying the series converges to 1 is like saying if you could add up infinitely many terms, you would get a 1. But can you actually add up infinitely many terms? That's exactly what Zeno is questioning. Using the answer to the question as a premise in your solution is circular. Let me put it differently. The mathematical limit is defined as the value that the partial sums approach but never reach. The limit of the sequence 1/2, 3/4, 7/8, 15/16 is 1, but no term there is ever 1. You never actually reach the term 1. So how does the runner do what the sequence can't do? How does he arrive at 1 if every step in the process only gets him closer but never gets him there? The philosopher Max Planck made this vivid. Imagine an infinity machine that does task 1, task 2, task 3, and so on, each one faster than the last. The series of task time converges, so the machine finishes in a finite time. But Black asks, describe the state of the machine after it's completed all the tasks. You can't specify it by looking at any task in the series, because there's always a task after it. The series has no last term. So, what grounds the final state? And this is the deep problem. It's not about adding fractions. It's about how an infinite process can have completion when, by definition, an infinite series does not come to an end in its own terms. Some philosophers think this is where Aristotle's distinction that we already saw on a previous video comes into play. Remember, Aristotle said there are two kinds of infinity, actual infinity and potential infinity. The runner doesn't actually complete an infinite number of steps one by one, checking off an infinite list. Rather, the distance is potentially divisible into an infinite number of parts. You can always describe a smaller sub-journey, but the runner does not perform each division. He just runs. On this reading, the paradox arises because Zeno treats potential divisibility like actual division. The room can be divided into half, and then that half into half, and so on. But the room is not actually divided into an infinite number of parts. The runner crosses one continuous distance, and we can describe the crossing using as many subdivisions as we want after the fact. So, who wins? Well, it looks like the paradox is still doing its work 2,500 years later. It forces us to confront a genuine tension on how we treat space, time, and the infinite. If space and time are continuous, infinitely divisible, then any motion requires crossing infinitely many sub-intervals. How is that possible? Calculus gives us a mathematical model that works, but it doesn't by itself explain how the physical act is possible. If space and time are discrete, they're made up of indivisible units, then the paradox dissolves, because there is a first and a last step. But then we face a different problem. How do you move between one unit and the next without passing through the space in between them? And anyway, modern physics treats space and time as continuous in the first place. And if you go with Aristotle and say that it's only a potential infinite, you have a powerful response. You do have to explain what it means to be only potentially but not actually divisible. That's not as easy as it sounds. What I love about this paradox is it sits square in the middle of philosophy, physics, and math. Mathematicians say, we've solved it, the series converges, you're welcome. Physicists say, people move, we see that it's obvious, so there's something wrong with this paradox, we need to find out what that is. Philosophers say, great, but nobody's actually explained how an infinite process is completed, and they're all partly right. The dichotomy paradox is one of the deepest puzzles in the history of thought. It has been inspiring and tormenting thinkers ever since the 5th century BC, and it's still generating serious academic debate today. Next time we're going even further down the rabbit hole. We're going to ask, are some infinites bigger than others? It sounds insane, but George Cantor proved that there are, and it changed mathematics forever. You don't want to miss that one, so make sure that you like, subscribe, comment, and hit the notification bell, and I'll see you in that video. Adios.